Today we're going to be talking about the basic waveforms and harmonics. Hello everyone, and welcome to WavSpot. For those of you who don't know me, my name is Austin Knaus, and I've been working with audio for over 20 years now. The first job I ever had was as a radio station engineer for WVLP 98.3 FM, which is a small college town radio station in Indiana. Over the following years, I made my way into electronic music production, as well as live performance as a touring DJ, opening for labels such as Intricacy, Mousetrap, and Dirty Bird. I've also played music festivals such as Dance Festopia, Backwoods Music Festival, Spring of Music Celebration, and Impact Music Fest. After live events took a hit in 2020, I ended up selling my entire music studio and starting a more stable career path as a technology specialist for Shure microphones. I also represented a multitude of other brands such as Denon Professional, Rain, Listen Technology, LEA amplifiers, and Klipsch speakers. Now, here in 2024, I fly all over the USA commissioning C-suite and executive level conference rooms for some of the top ranked Fortune 500 companies, and I didn't even finish high school. I'm taking everything I've learned along the way and boiling it down to the basic fundamentals in hopes to give you a fast track to a better understanding of the world of sound. So, let's dive in. In the last few lessons, we learned about frequencies and the different characteristics that frequencies have, such as a positive amplitude or a negative amplitude, and how that correlates with polarity. We also discussed phase and the relationship between two different frequencies at any given moment, and whether they are in phase or out of phase, and how that can actually change what we hear. So today we're going to look at the different basic waveforms, and in total there's 5 of them. There's a sine wave, there's a triangle wave, there's a saw wave, there's a square wave, and there's a pulse wave. Before we get too deep into the basic waveforms, we need to get into harmonics and understand what harmonics are, or what a harmonic is. So what is a harmonic? So at its core definition, a harmonic is a whole number multiple of a fundamental frequency. What does that mean? So what exactly is a fundamental frequency? The fundamental frequency is the lowest frequency relative to its harmonics. Let's take 60 hertz, for example. A whole number multiple would be 2, 3, 4, 5, 6, 7. The second harmonic, the third harmonic, the fourth harmonic, the fifth harmonic. So if we take 60 hertz and we multiply that by 2, we're now sitting at 120 hertz. And that's going to be our second harmonic. 60 is the fundamental frequency, and 120 is the second harmonic. If we were to multiply 60 times 3, we'd now be looking at 180 hertz, and that's going to be our third harmonic. So what if we wanted to try to find the fifth harmonic of 60 hertz? Well, it's easy. Just multiply 60 times 5. And now we're looking at 300 hertz. 300 hertz is the fifth harmonic of 60 hertz. 60 hertz being the fundamental. In this example, we just picked 60 hertz arbitrarily. Essentially, the fundamental frequency is whichever frequency you pick, and then multiplying a whole number, 2, 3, 4, 5, 6, 7, by that fundamental frequency, you then find its relative harmonics. And every frequency has harmonics. So for another example, let's look at the note G4 on a piano. This note relates to 391.99 hertz. I did some math. I don't know that off the top of my head. I picked this number because it's already kind of relatively high. It's not a low number like 60 was. So if we take 391.99 hertz and multiply that by 2, we're now looking at 783.98 hertz. The third harmonic, multiplying 391.99 times 3, we're now looking at 1,175.97 hertz. So essentially we can multiply our fundamental frequency infinitely all the way up to infinity. But again, we can only hear from 20 hertz to 20,000 hertz. For our 391.99 hertz example, the highest harmonic we would be able to physically hear would be the 51st harmonic, which would be 391.99 times 51 equals 19,991.45 hertz. This means if we went to the 52nd harmonic, we would lose the ability to hear that because it's now above 20,000 hertz, or above our physical ability to even hear that frequency. So for the 391.99 hertz example, we can get all the way up to 51 harmonics before we lose the ability to hear it. If we started at a lower number, like that 60 hertz example, we would be able to achieve more harmonics before we reached the top. It's relative. The higher the frequency already is, the less harmonics we're going to be able to hear, simply because of physics and the way we hear. Okay, so now we know what harmonics are. We know that they're a whole number multiple of a fundamental frequency. Let's get into waves. Like I said earlier in this video, there's 5 basic wave shapes. We have the sine wave, the triangle, the saw, the square, and the pulse wave. Now let's get into the differences of those. The sine wave is considered a pure tone because it doesn't have any harmonics at all. This is also the wave that we're most familiar with because it's what I've been using to show you and demonstrate the different characteristics of frequencies, such as the positive polarity and the negative polarity. The sine wave, or the sinusoidal wave, is the most common. It's the purest. It's the base. Essentially, it's a fundamental frequency, is because there's only one when it comes to a sine wave. So next, let's look at the triangle wave. Other than the shape of the wave, the main difference between a sine wave and a triangle wave is that the triangle wave actually has harmonics. It's not all of the harmonics, though. It's only the odd numbers. So the 3rd harmonic, the 5th, the 7th, the 9th, the 11th, and so on into infinity. What's important to know, though, is that not only does it contain harmonics, but the amplitude of each harmonic is inversely proportionate to the number of the harmonic. We're getting into some math here. As the number of the harmonic gets higher, the amplitude lowers. The actual equation to figure this out is the fundamental frequency divided by the square of the number of the harmonic. I'll put the equation up here so you guys can see it. The higher the harmonic, the more rapidly the amplitude is decreased, and specific to a triangle wave. Don't worry, we don't have to memorize equations. We don't have to do math to work with audio unless you want to do the math and the work that you're doing with audio requires it. The next wave that we're going to talk about is the saw wave, and personally, this one is my favorite. The saw wave contains all harmonics, both even and odd. This means that there's more frequencies happening at one point of time in regards to the triangle wave, because the triangle wave only has the odd. The saw wave has both even and odd. The amplitudes of those harmonics are proportionate to the number of the harmonic. Next, we have the square wave, and you probably see how it got its name. It has an instantaneous change in amplitude, both positive and negative. To me, I like to think of a light switch. The light is either on or the light is off. There's no in-between state. It's either on or it's off. Much like the triangle, the square wave only contains the odd number of harmonics. The difference between the triangle and the square is that the triangle is inversely proportionate to the number of the harmonic. The square is proportionate. This means that we can hear more of the higher range harmonics in the square wave than we can in the triangle. Last but not least, we have the pulse wave. The pulse wave has the same harmonic characteristics that the square wave does. The big difference, though, is what we call its duty cycle. In other words, how long is the positive polarity active for? If we look at our square wave, we can see that it's pretty much 50-50. If we have a single cycle and we cut it in half, then we have a positive portion and we have an equal negative portion. With the pulse wave, however, the positive portion shrinks and the negative portion grows. It looks more 20-80, or it could be 40-60. The difference is that it changes in size. You'll also see this called PWM, or pulse width modulation, because we are modulating the pulse's width, or how long the duty cycle is active for. So, per usual, it's one thing to talk about it and explain it and tell you what it is. It's another thing to actually show you. So our first tool up here on the left will allow us to see the waveform. This tool shows us the frequencies from 20 hertz all the way up to 20,000 hertz. It allows us to see whether it's a low frequency or a high frequency, with the lowest being all the way to the left and the highest all the way to the right. So with a combination of these two tools, it allows us to actually see the audio that's going on. Let's look at the sine wave first. If you remember, as we discussed, a sine wave is considered a pure tone. There's only one frequency in a sine wave. There are no harmonics. And so if we play the sine wave, we can see roughly here around 200 hertz that we only have one frequency. Now, if you remember the triangle wave consists of only the odd harmonics. What that means is that there's going to be odd multiples of the fundamental frequency. So if we're looking at the spectrum analyzer, we should be able to see a lot more frequencies above this 200 hertz mark. Let's take a look at the triangle. You can see all these extra frequencies, and they rapidly decrease. So the fundamental frequency is louder than the rest of the harmonics. Now let's look at the square wave. Remember that the square wave also only contains the odd multiple harmonics, just like a triangle wave. The difference is that the amplitudes don't decrease as rapidly. Here's a square wave. You can see that the amplitudes are pretty much level across the board until we start getting up to the high range. So if we let a triangle wave play into a square wave, we'll notice only one thing. The high range harmonics only go up. Same frequencies, only increased in amplitude. That's the difference between a square and a triangle wave. Now let's look at the saw wave. But remember, the saw wave contains both the even and the odd harmonics. So all of the spaces that you saw with the square wave and the triangle wave will be filled up with a frequency. So check out how full this sound is. There's a lot more harmonics. So let's put a sine wave, then a triangle, and then a square, and then a saw, and we'll see how the frequency spectrum fills up over time. Isn't that cool? Let's watch it again. Let's look at the pulse wave for a moment. We can see here that it looks just like the square, but its duty cycle, or the time the positive polarity is happening, changes, and we're able to move the width of that pulse. Often we'll see this called pulse width modulation, and we can hear it happening. A square wave is pretty much 50-50 within its cycle. The pulse wave varies between essentially 0 and 100%. We can see that the time it stays positive slowly goes away. Okay, so what is a harmonic? Harmonics are frequencies that are whole number multiples of a fundamental frequency. A sine wave is a pure tone or a single frequency. It's essentially the fundamental. A triangle wave consists of its fundamental frequency along with all of the odd harmonics above it. A square wave also consists of a fundamental frequency and the odd harmonics. The saw wave consists of the fundamental frequency and all the harmonics, both the even and the odd. The pulse wave, or the pulse width wave, is characterized by its duty cycle, which means the length of time that it stays in its positive polarity in comparison to the length of time that it stays in its negative polarity. When you overlap frequencies, depending on whether they are in a positive or a negative polarity, they have either constructive interference or destructive interference. This is why the wave changes shape. If you found any of this information useful, leave a like and hit that subscribe button. If you guys want to learn more about the topic, feel free to head over to wavespot.com or just join the comment section below.